Hello, ladies and gentlemen. My name is Dennis Otibar. I'm a research assistant at the Ruhr University in Bochum, Germany. And today I'm going to tell you some results concerning our researches about the effect of shape memory alloy, SMA, training on variations of production process parameters. First of all, I'll give you a short outline of my presentation. So I start with the motivation and give then some information about the standard manufacturing process of nickel titanium wires. After that, we go to the SMA training. So SIMT is a special kind of training. I will tell you in detail. And after that, I explain the experimental procedure, and after that, the results. And I will finish with conclusions and outlook. So, first, motivation. Shape memory alloys. Yes, we know that they have the ability to remember a previous imprinted shape. And these alloys, they react sensitively to small variations in the production process. So, for example, if the wire in the wire drawing process gets too high, the temperature gets too high due to some factors, the characteristics of the SMA might be different to or as they are expected, especially concerning the phase transmission temperature. Excuse me, the temperature when it's activated. Yes, transformation, yes, sorry. And so this might be a cause that the reproducibility of the SMA characteristics is not always as you want to have it. So it's a subject to high demands. And after the whole wire drawing process, there's an SMA training that can be done afterwards, and to imprint the characteristics for this material. And now we had the questions if variations or damages caused in the production process, especially the wire drawing process, can be compensated with this training process. And first I'll give you some information about the manufacturing process, short outline. So basically, this is the laser pointer. Ah, yes. Okay, so we don't regard the process of the manufacturing of the ingot. So we start with the wire drawing, and after a degree of deformation up to 40%, there's normally an intermediate annealing, about up to 800 degrees Celsius, and then to make the material deformable again. And so then you repeat this process until you have the required diameter of the wire. And as a last step, you have the final heat treatment. After this, you could stop it, and the nickel titanium wire already has the shape memory characteristics, so that it can, for example, you have a wire and you can stretch it maybe for some millimeters, and if you heat it again, it will go to the first length. And so you have this. Yes, you have this after the final heat treatment, but the problem is that when you have more cycles of activating, the wire might get longer. So if you start with a wire of 100 millimeter length, so it might get, after 100 cycles, activation cycles, it might be about 104 or 105 millimeters length. So that's why the SMA training is made, so that you make a lot of cycles, of activation cycles, that you don't have this kind of drift, and afterwards you can apply it in technical or mechanical things. So and with a high reproducibility. And yeah, so this is the point what we are what we have investigated now. And so now we come to the training process. We investigated the SIMT training, which means stress-induced martensitic transformation. So you have an SMA wire that is mechanically loaded permanently, and you are in the martensitic phase, and then you heat it up above the austenite finish temperature, AF, and it has already the same load. It's stressed again all the time, and after that you cool it down, and so you repeat it for several cycles, maybe up to 100 cycles. It's kind of literature we were investigating, or we were reading, and it was about 100 cycles. So the SIM training is for minimizing running-in effects of SMA devices. And for that we have a kind of test rig and the requirements were that we have wire diameter from 0.3 to 0.8 millimeters that can be trained with this machine, and heating temperature up to 400 degrees Celsius, and the design for stress up was up to 400 Newton per millimeters squared, and regarding 0.8 millimeter wire diameters. And so this is our test rig in our laboratory, and yes, for industrial applications it must have been constructed in a different way. And so yes, this is what we can see here. And as an experiment procedure, we had two different produced wires. On the one hand, we had the kind of good wire, SMA wire, the wire A. It was the alloy H, so from the manufacturer called SAS getters, but we don't know how exactly they produce the wire. We just know that it is a really high quality wire that is already used in many technical applications. And yes, on the other side we had our kind of poor wire, and it was also the same alloy when we started with the coil, but then we had different, or we had a partner that could draw the wire for us, and we told him just be very rough to it and destroy it kind of. And so these are the drawing parameters. So we made it up to 0.3 or 30% the degree of deformation, and with the it's not very high, the wire drawing speed, but for this application it's okay. And yes, I will not mention all the parameters now. We had an intermediate annealing process with protective gas and water quenched, and as the last step also a final heat treatment with 500 degrees Celsius, 20 minutes. But after that, it was followed by a SIM training. The training parameters were the same for both, for the good and for the bad wire. We had a annealing temperature of 180 degrees Celsius, annealing time of 10 seconds. So the wire from this point to this point, it needed 10 seconds. This is our tube for heating, and 80 cycles. And the training stress was about 175 Newton per millimeter squared. So the same training parameters for both wires, type A and B, were applied. And after that, we made activation tests. So they were proceeded in a climatic chamber for 10 cycles. And yes, temperature was 20 to 120 degrees Celsius. And these are the results. First, for the good wire with our training. So you see this is the gray line. This is, yes, an optimum wire. of SAS getters as it has to be. It makes a way of about, or displacement of about 4 millimeters, and our wire had a small drift directly in the first cycle of 1 millimeter, but then it had the same behavior. And now the poor wire, we see it didn't show not a real SMA effect. So when it was heated up, it got longer, so it was really destroyed. So you see, it's not the way it should react as an SMA device. And so we can say that variations of production process parameters cannot be compensated by a subsequent SMA training as a first result. So we just saw some SMA training with same parameters was applied on wires made by different parameters, and yes, the SMA wires were tested and determined their SMA characteristics. Despite the same training parameters, the SMA characteristics are strongly deviating, and so that our conclusion is that variations of the production process parameters cannot be compensated by a subsequent SMA training. So maybe as an outlook, we can make some investigate some different production process parameters, or use another training method or training parameters that can be investigated in the same way. Thank you very much.